All right. Well, everyone, thanks for joining another ToloTalks. Uh, I'm Adam Farley, so I'm the Northeast Regional Sales Manager, and I have Tim Najelski is going to be helping out today as well. He's one of the apps guys, and
Good morning, everyone.
just as an inside joke, we are great ones. So for you that know us or don't know us, we considered the great ones at Tolomatic. All right, we're going to go through some pressing applications today, just some do's and don'ts relative to pressing. Uh, Cover some old technology versus going electric servo. Tim's going to talk about ins and outs of load cells and sizings, and then we'll conclude with some questions after that. All right, so we'll jump right in here. So here's an example of some early manual hydraulic press. You know, you see these, still see these today in shop floors, and you know, it's typical manual operation, low duty cycle, vertical orientation, downward. So downward force typically, and typically these type of platforms they're short strokes. You know, they're probably pressing in bearings, or they're doing small punch work or punching pins in, or forming. In that case, or doing some small part forming with these type of platforms. All right. Then we get another part of the other technology is this flywheel press, and we've seen this type of stuff. So this is something Tim can talk to, because Tim has actually worked on these platforms. So Tim, why don't you talk about this?
Yeah, hello, everyone. This is Tim with Tolomatic in applications. In my early days, I worked with punch presses of actually 5 to 10 tons. This rather complex machine has a large, heavy rotating flywheel, and when engaged when a clutch is engaged, this flywheel is going to drive this ram down into a die, which can basically punch holes or shape parts. This device here is it is a usually for a dedicated set of parts. It has a just one basically motion cycle dictated by the mechanics of the machines. There's no dwelling unit, or excuse me, the dwell is actually set by the human operating this here. And it's true, in the case of my working too, I was making greenhouse framework. And typically it took an entire complex die to make only one part. Then once you've made the number of parts, you'd have to shut the machine down, remove that heavy die that could weigh 100 pounds or 200 pounds, bring in a new die, and then you have to basically reset the machine, make sure that the downward stroke was not, jamming on the die too hard. Some dies were spring loaded, they're easier to work with, but some weren't, so you had to be really careful. The accuracy and repeatability had something to do with the setup of the machine. In my particular case, I had mostly spring-loaded things, so it wasn't that easy. It is a fairly expensive machine. Die sets are expensive. And the other thing I remember about it too was that it is there are definite safety concerns on a machine like this. You definitely don't want to get your fingers into that moving part of the machine. Let's move forward here. Okay, yeah. Okay, and then a somewhat more advanced press is a electrohydraulic, or a hydraulic manifold that's controlled by solenoid valves, can adjust pressures and speeds. and it can actually affects parts quality. There's an ideal punching speed. It is less complex than the flywheel-driven system, and perhaps somewhat safer. There is, however, high costs of running hydraulic pumps and the manifold, and it is somewhat of a maintenance issue. You have leaking hoses and seals. I've never seen a hydraulic system that didn't leak in some manner. The working area around this thing is often slippery hydraulic fluid, and I know because I have fallen a few times. Generally, it's a higher cost than the flywheel machine due to the maintenance of pump seals typically. And let's move forward here. And then we have the electric servo mechanical press. This machine is far less complex, the number of parts. A servo motor can adjust the move profile for basically speeds, distances, dwells. The part changeover can be really quick. One can just simply load a new program. It's ready to go. There is feedback, so one can monitor the consistency of the work you're doing. Yeah, I guess I already did mention we greatly reduced mechanical complexity. Let's see here. Let's move forward. Okay. Now, naturally, every system has its strong points and its disadvantages. In a servo mechanical press, you can typically not gain the extremely high pressing forces in the hundreds of tons that you can with a purely hydraulic. Typically at ToloTalks, using us for a reference, we have a 25-ton capability with the RSX 128, a 64 millimeter diameter roller screw, which is fairly colossal if you're familiar with our product. One of the initial challenges in all systems is that the length of a electric cylinder with a motor is significantly longer than a hydraulic cylinder that usually just sits on clevises. The upfront cost is usually something to consider. It is the cost is not only the equipment, it's also the training. The learning curves typically are involved with the programming. Every servo drive has some kind of a motion profile, and then there's often a PLC integrated with that to monitor it, to tell it when to move, to perhaps drive multiple actuators at the same time. And then all this drives and PLCs, all this electronic sophistication needs to be housed in a panel with significant physical wiring. Let's move forward here. And then there's enable, start motion, phone, software stop.
All right, I can take over here, Tim.
Okay. Go ahead.
So, next is we'll just talk about the advantages of going to servo mechanical. Of course, everyone knows we can size these going electrical, mechanical with our sizing tool. So what we're sizing can actually give you what we're producing. So if you're asking for a 20-ton press, we're going to give you a 20-ton press. Okay. Are we able to give you precision speeds in positioning with a servo motor with feedback? Yes, we can. Like Tim said, all of our higher force units come with a roller screw. So, you're looking at some high precision out of the roller screw as well. It's typically a, plus or minus 1,000 these days. The other ability is this full working stroke at all positions. So, adjustability, part changeover seems to be a big driver for making these type of, these conversions. We can be less expensive than a hydraulic press. I think when it comes down to the ROI, that basically you got to look at. So you're running the pumps, compressors, the maintenance part, the high scrap from going, hydraulic because you don't have feedback. We're going to be at the long run, we're going to be cheaper, and there's going to be a lot more cost advantage there, especially on some smaller presses as well. And like I said before, we had excellent accuracy, repeatability, and just getting back to the low operating cost and figuring out the ROI, and just my opinion, just getting around, this ends up being sort of a facilities sell in some cases. You're talking to the facilities guy at a plant floor or a user, you're talking to that guy as well about these operating costs. So don't forget to look at the facilities engineer in these plants. Other advantages, this closed loop, right? So feedback, motor encoder, looking at current draw, having load cells to, maybe your part can be, you're running at certain forces with certain materials, or you're switching materials, so you can really dial in your press requirements going electric. We've got all these nice bells and whistles, you might as well use them. And again, it depends on the application, if it is, current or load cells, or you're just, you're tracking these things through an HMI or your PLC, so you're actually pushing out good parts. All right. Also, we've done this. I've actually done this locally. When you're doing some stamping applications where you're doing multiple hits on a part. That's available. Again, programming a motion profile is key to key to these conversions too. Typically, these hydraulics are, you want to go back and forth. It's a positioning nightmare from that standpoint. And then, the system itself, just having fewer components on the electric side is going to be better. It's going to be a lot easier from a maintenance standpoint. And then, we can, in some cases, just be a lot faster on cycle times. Okay. Next, like I said before, fewer components, so there's less potential failures. So I think Tim mentioned it earlier. We got, you're not looking at seals and hoses breaking. It's a constant maintenance nightmare from what we've seen. And then you can track. What's nice about the drives today is you can actually start looking at failures. Maybe you can look at a motor that's actually starting to draw more current, because maybe it's starting to fail in some cases, or so that could, you're identifying potential problems there. From the screw side on the actuator, we're giving you grease ports to actually, we can set up some sort of greasing schedule with you, and that's either looking at duty cycle, or in some cases I'm telling customers, if you have an HMI and you can program the HMI to have a certain amount of cycles, and then a light goes on and that tells you, okay, you've run so many thousands of cycles, it's probably time to give that roller screw a grease. And that would be running it, greasing it, not over greasing it, and then running it through its stroke a few times, just so the grease gets back into the planetaries on the roller screw. All right. Again, upfront costs. Yeah, again, it's the ROI. You look at the panel assembly, these are usually 230, 480 volt systems. So, you're supplying just an actuator, a servo motor, and probably a gearbox, but, you're supplying us a panel as well. And some of these components can be a little expensive out of the gate, but, I think you're selling the ROI at that point. All right, and then we're going to talk about roller screws and ball screws in a minute, but in some cases, some of these smaller press applications or benchtop, we're looking at, ball screws are also fine for this type of maybe low duty cycle, smaller run products that are being pressed. All right. Tim, you want to take this over?
Sure.
Okay.
The technologies that Tolomatic provides are ball screws and the roller screws. Now, the ball screw is basically a moving part with recycling ball bearings. Your drive is connected to this flange on here, or in this case, rod. And ball screws are been around for a long time. They're relatively inexpensive. There are a wide range of forces available. Well, Mac, we go from hundreds of pounds into up to 13,000 pounds. And they are maintainable with predictable lives. The roller screw, on the other hand, is a precision ground device, a set of rollers wrapped around a central screw in a what we call a planetary configuration, and then with a case around it. Now you'll note that the roller screw has a lot more surface contact with the screw than the ball bearings of the ball screw do. This enables the roller screw to generate a lot higher forces, and also, if used correctly, can have a lot longer life. This dynamic load rating is much higher than the ball screw. The principal concern with a roller screw is that this mechanism does not overheat. We don't want to overheat and lose our lubrication. And we have software to deal with that too, which we'll get to in a minute here. As far as positioning, relatively good on each technology. The initial cost of a roller screw will be higher than a ball screw, but then that can be the trade-off can be a much longer life. Let's move to the next one here. Okay. Monitoring force is very important in these applications here. Two of the primary ways to do that are using the load cell and then monitoring the drive current. We do mention two types of load cells here. The piezo is probably the most common. And these can be either compression or it can be tension. So these are actually higher precision force feedback. Monitoring the current in a servo motor typically gets you within 10 to 15% of the ideal target here. Let's move it on here. Okay. So when Tolomatic gets an application here, basically we get, we're probably going to get like a maximum force that we need, a movement, and a cycle rate. So we take these, and then of course we also ask questions, orientation, life expectancy, and we're often asked, how do you maintain these? And then of course the accuracy and repeatability always comes up, the quality of the work that you're doing here. In this particular 15,000 pound we deployed an RSX 96, a 12 millimeter per turn roller screw. We were able to get 12.8 million cycles out of it. There is an easy estimate, or an easy formula to estimate life. In this particular case, it was about 6 years. So that lifetime of the roller screw can also be measured against a ball screw with a load rating of say half of this. In this particular application, once again we use the typical piezo load cell. Okay, let's move it forward. Okay, so ToloTalks sizing software is used to right size a electric high force rod actuator here. What we can do is in our motion profiler here, we can graph the movement and when the load is present. Sometimes the load's only present on like an extend or part of an extend, and there's hardly anything on the retract. So the software can come up with an RMS value. Then that RMS value is useful for calculating life. In this particular case here, 16,000. Okay, now, so not only calculating the RMS force is really valuable, the software also does thermal modeling to make sure that that roller nut doesn't exceed the temperature that would cause it to lose its lubrication. And then one other sometimes overlooked parameter in an application is the axial loading on an actuator, or buckling force as we call it. The sizing software checks all these parameters for you, so it'll warn you if you go outside the bounds. This way we get basically a right size for the amount of work we're doing and the life expectancy. Let's move ahead a little bit. And here is an example of the errors that the sizing software can detect. Thermal limit is exceeded. So to compensate for that, it tells you to put in extra dwell. Okay. Now the software, of course, also gives you torque speeds, and inertia values as well for your application. In this particular instance here, it was reported that we needed a 47 horsepower motor, when they were actually using a 10 horsepower. But anyway, this is a way that our sizing software right sizes the actuator for the application.
All right. Thanks, Tim.
Okay.
All right. So just gonna close this off the next few slides here, but just to give you guys just the overview of our rod style product line, and you can do some sort of pressing type applications with all these rod styles. IMA, the IMA stainless steel, even if you're pressing or pushing food or in some case filling, you're pressing, you're pushing on some of the washdown products. Like again, RSA, ST, HT would probably be the better model on the pressing applications. And then we ERD as well. I have a customer that does small bearing presses. He only needs with 100, 200 pounds, and he does them with ERDs. And then what we've been talking about mostly with this, hydraulic replacement of the larger RSXs that we're promoting for hydraulic replacement. And these are giving you, RSX 80s, 18,000, and then up to the 128 that we talked about, it's 50,000 pounds of force. All right. And then, keys to success. We've all sorts of stuff on the website, guides, tech notes, and videos. Everyone's been seeing all the ToloTalks, but there's also, a great section of AppWin industry wins that are constantly being updated. So, you know, check out these links, go on the website. If you can't find any of this stuff, please, you know, contact your local RSM or any of your tech and apps guys. All right, and they can get you direct you in the right direction. We do have other videos, so YouTube videos as well. And there's just a little overview here of all the, you know, not just our blog, but we do have a YouTube, a lot of content on YouTube regarding just about everything. If it's not motor mounting to, you know, some of our ToloTalks, as well as, you know, the installation processes and stuff that we do on YouTube as well. That's all available. All right. And then just quick summary on what we're doing for pressing, you know, looking at cost and, you know, looking at the technologies. You know, we're all seeing this right now. It's this conversion from hydraulic to electric. We also see it on the pneumatic side too. Let's not forget about the pneumatic stuff. It's all pretty similar. You know, production rates, I don't know anyone that wants to run slower these days. And, you know, going servo electric, you know, you get high production rates. Again, the ROI is flexibility, right? So customers want to be able to run different products and have that flexibility. You know, we can adjust strokes with servo electric. You know, it's a lot more flexible through, you know, an HMI program for an operator. And then, you know, the bang for the buck from you know, good parts versus bad parts is feedback. So, you know, your positioning and your accuracy feedback through servo electric is just far superior to hydraulic all day long. Other attributes, yeah, noisy, dirty. We mentioned the leaky hoses and the slip and falls type of safety concerns with hydraulics, and then hydraulics getting on, you know, basically contaminating parts too, you know, depending on what the parts are. Again, clean, efficient, going servo mechanical. And then, you know, just talking about parts quality, as I did before, you know, you're gonna get much better parts quality out going electric. All right. And then just a couple things. You know, we're here to help on any of these projects and applications. So feel free to reach out to any of us RSMs or your tech and apps guys for any future applications, or if you just need to, you know, maybe you're going through a plan and you saw a target and, you know, you need some information, and go talk to either the, you know, the plant floor guy or the operator that's running the machine, to get them some more information and possibly doing this type of conversion.